Good evening. Welcome to tonight's MLA Sheep Productivity and Profitability webinar. The title of tonight's webinar is To Lime or Not to Lime. My name's David Brown and I work with the webinar coordinators, Home Sackett, and I will be your webinar host this evening. Quickly before we move on, for those who are new to the webinar platform, you'll have this control panel on the right hand side of your screen. Please collapse and reinstate it using the red arrow there. You'll be able to hear us, but we can't actually hear you. Please type all questions and comments in the questions box that's available to you there. They'll be logged chronologically, and the presenters have kindly offered, and an expert panel of soil and pasture scientists have agreed to participate in a robust question and answer session at the end of this webinar. So put your questions in there, and if you want your questions answered first, then I recommend getting in and put them in as soon as you can. I just want to note, please make your questions clear and concise. Sometimes if you are too hurried when you put them in, or they don't quite make sense, it makes it hard for us to interpret and answer correctly. So just take some care when you're doing that. Before we move on with tonight's presentation, I just want to make everyone aware of next week's presentation. Same day, Wednesday, after Easter, on the 4th of April. And it's going to be a webinar on nitrogen and gibberellic acid, the principles, production and profit for prime lambs. And that's going to be presented by Basil Doonan of Macquarie Franklin, based down in Tasmania. Tonight's presenters are going to be Dr. Jim Virgona and Nathan Ferguson and Dr. Jason Condon. So Jim's our principal presenter. He's a dynamic presenter with a mix of experience and intelligence, humour, and I don't think Jim will leave you in two minds after this evening's presentation. He's a touch footy player, and a very good one at that. And aside from that, he's been involved in pasture agronomy and performance for the last 25 years, working with New South Wales DPI. He's worked as an academic at the Charles Sturt University, and now he's an independent consultant, spreading his business out around Riverina and the southwest slopes and beyond if required. He has an impressive research CV and years of on-farm experience, and so there's none better than Jim to present to us on this complex issue of liming this evening. Nathan, he's been located up at Tumut, and he's part of the same business as Jim. That's called Graminus Consulting. Jim and Nathan are business partners, and Nathan's been providing advice to the ag sector since 1996. He's very well versed in all things agronomic. He's worked in retail agronomy for 3 years in Wimmera, and with the New South Wales Public Service as a district agronomist at Canamble, Moree and Tumut over a 14-year period. Nathan's a very practical and lateral thinking person, and he's going to provide a powerful second perspective to Jim's in this evening's webinar. And lastly, a wildcard entry, and we're very lucky to have Dr. Jason Condon with us this evening. He's the third panellist and probably the better looking of the three. He's has an honours in the amelioration of subsoil acidity and a PhD investigating the effect of nitrogen transformations on the formation of acidic subsurface layers in grazed pastures. With this, Dr. Condon brings a level of intellectual clout to the MLA webinars we have not enjoyed before. He is employed by as a lecturer of soil science at Charles Sturt University, and he has currently projects both domestically within Australia and in the Mekong Delta of Vietnam. With that, I'd like to welcome the delivery team to the webinar, and I'll just pull up. Jim, are you with us there, Jim?
I am with you.
Good evening, Jim.
Yeah, I just clicked show. Show my screen.
Perfect, Jim. Just
see it?
We can see your screen and we're ready to go.
Right. How do I get rid of all this stuff on the right-hand side? I don't.
You just press that red button, Jim, and it'll collapse the control panel.
Ah, good-o. There you go. Thanks a lot, Dave, and good evening to everybody, and thank you for joining us tonight. The topic given to us, before I get into the topic, I just have to correct Dave on one thing. Jason Condon is hideously ugly, but apart from that, he's quite a good fellow. Right, so what I wanted to say was the context tonight. So the question is to lime or not to lime, and the context mainly of relevance to prime land producers will be permanent perennial pastures. So some might be a bit disappointed in that, but I think there's probably more uncertainty in that area, and it's probably worth us delving into it a fair bit. And unfortunately tonight, the answer to that question is so often going to be basically a two-word answer, and that one is, well, it depends. And so tonight, essentially, we're going to be sort of spending the rest of the whole talk essentially understanding why it depends, because it is not as straightforward. The decision to use lime is nowhere near as straightforward as the decision to use a fertilizer or to implement some other simpler form of technology. So first of all, let's get some ideas in our head about exactly what we're talking about. So the first one is, what is lime? Well, lime, as we commonly know it, is ground up from limestone. It's chemically, it's a molecule of calcium and carbonate. So lime is, you put that together in a single term called calcium carbonate. And the symbol for that, for pure lime, is below. So we see we have a calcium and a carbon and an oxygen, and in that ratio, CaCO3, and that is lime, or that's what we're going to refer to as lime tonight. Now, so that's pretty simple. There will be a bit of chemistry tonight, so it might get a bit challenging, but I'm sure we'll find our way through it. So the next one is, what is soil acidity? Well, it's the simplest way for me to tell you is it's a concentration of hydrogen ions in a solution. A hydrogen ion, we might also at times not just use another term, but it's exactly the same thing. It's a proton. Essentially, it's a hydrogen atom that's lost an electron. It's the best way to think of it. So that's why it's denoted by a H and superscripted by a plus. We measure the concentration of hydrogen ions on a log scale and call it the pH. So you're all familiar with that term, the pH. So you know that a pH of below 7 is acidic, but pH above 7 is alkaline, and of course the pH at 7 is neutral. So that's just a scale on which we understand which we express the concentration of hydrogen ions and therefore the acidity. Now, many of you, well, especially those who've been around a while, a lot of it, when a soil is sampled now and an extraction is made, it's common now, I think everybody does it, to extract in a solution of calcium chloride rather than once upon a time it used to be water. My colleague Jason Condon will explain.
Thanks, Jim. Yeah, so basically, to measure the pH, you have to have an electrode in a solution, and so you add soil to water in a given ratio, and that's what happens in the lab, and then the pH is measured, and people say, well, that's great, except that plants don't grow in pure water, they grow in a soil solution that has other nutrients in it. And so when we add calcium chloride, the actual amount of calcium chloride we add gives a salt concentration in that solution that's pretty much the average of topsoil salt concentrations. And so the pH that you get from that calcium chloride measurement is much better aligned with what a plant will experience growing in that soil. And so it kind of relates better to plant growth.
Thanks, mate. Excellent. And so, the next one is, I mean, if you almost remember nothing else from this talk tonight, I'd like you to remember this slide. It's the next one. Oh, yes, that's right. And talking about the water calcium chloride thing, pH extracted in water is usually around 0.8 of a unit higher than it would be in calcium chloride. Let's go to the next one. So lime neutralizes soil acidity. Now, when we add lime, it does that by reacting with the hydrogen ions, those little H pluses that we saw before. But the equation of this is important. So you'll forgive me for the chemistry, but here it is. So over here, we've got calcium carbonate. We already understand that to be lime, and that is reacting plus a couple of protons or hydrogen ions, right? And when they react together, they form water, carbon dioxide, and some calcium ions. Now, you've got to understand, it's very, very important to understand the last point here, down the bottom. It's the carbonate in the calcium carbonate, that is the carbonate in lime, that reacts with the acid, okay? It's not the calcium. Otherwise, other calcium products would neutralize, like gypsum, would neutralize pH, and they don't. So the reason, it's the carbonate in calcium carbonate, i.e. lime, that actually does all the hard work. So if there's nothing else you remember from tonight, I'd really like you to take that away with you. If all the lime reacted and was pure, then for every kilogram of those protons or hydrogen ions, we would need 50 kilograms of lime. That may become important a little bit later when we look at some calculations that have been done. And therefore, when the lime reacts, it takes more of those hydrogen ions, if you like, it locks them up, right, or reacts with them. So their concentration in the soil declines, therefore the pH of the soil rises. I read somewhere, Keith Hellier wrote it for some reason, but soils are usually, look, after you've put lime on, soils can still be on the acid side, i.e. even a pH less than 5.4, which was somewhere the official definition of an acid soil. Don't ask me where it came from. But the whole thing is, it's less acid than it was before you lime. So when we lime, we don't get rid of all of the hydrogen ions because there's such a great big store of them in the soil, but we, to some extent, we neutralize them, and therefore the pH rises. Now, the other thing I'd like you to get before we get onto some of the data that we want to talk about is what causes acidity. So Jason and I are going to do this, and just quickly, there are three main causes of acidity. One is got to do, the first one I'll talk about very briefly, and that's got to do with the nitrogen cycle. So now up on your screen, you should see this complicated looking diagram. I'll try to uncomplicate it as much as possible for you. But essentially, if we just start with the plants, all right? So you will know in your permanent pastures that it's the legume component that fixes nitrogen, and the grass, and also along with it is the grass component. When either they're eaten or they rot back into the soil, they basically contribute to the when they're eaten and through dung, I meant to say, or when they rot and die into the soil, they contribute to the soil organic matter. Now, just watch these little hydrogen ions because they're the things telling us about the acidity. As the soil organic matter breaks down, a process we call mineralization, then actually a proton or a hydrogen ion is used to form what we'll call ammonium N. You can look at the formula, that's all very nice. As that ammonium N gets converted to nitrate, a form that plants more readily take up, then it gives off two hydrogen ions. If that nitrate, now this is very important now, so we've got this little cycle going around. Now, if that nitrate is taken up essentially where it was formed, then the plant basically also uses another hydrogen ion. So you can see two are used, two are produced. It's a balanced sort of system, right? But sometimes, especially in winter, where we get an excess of rainfall, then some of that nitrate, which is highly soluble, can be leached to another part of the profile, and even beyond the rooting depth of the pasture, in which case this hydrogen ion doesn't get used. And so the net effect is we've had a slight build-up of hydrogen ions in the soil and therefore a decrease in pH. Now, that's as much as I want to say about that. So that's, and we'll see later on, but that can account for about 30 to 50% of the acidification that goes on in a soil. Jason will take over now to tell you about the other causes of acidification.
Yeah, so that's a nitrogen cycle process, and then the other two that we'll talk about deal with carbon in soil, and that's product removal and organic matter accumulation. And so basically with the carbon cycle, if you think of a plant, they're going to take up nutrients, and some of those nutrients are positively charged and some are negatively charged, and a plant will try to maintain its internal charge as being zero, and that has implications for pH. So if we have a plant, and Jim points out that there aren't too many palm trees around in this area, and yeah, that's fine, but it's a plant. When plants grow, they take carbon dioxide and water out of the atmosphere and they turn it into organic matter, and that's plant growth. When they take up cations, so this is your ammoniums, your calciums, magnesiums, sodiums, potassiums, the plant's taking on a positive charge, and so to maintain its balance, its internal charge balance, it will excrete something that's positively charged, and that will be one of those hydrogen ions. And so it actually excretes acid into the root zone, making the soil acid. Now it does that by part of that organic matter basically losing one of those hydrogen ions and pumping it into the soil. When it does that, the organic matter that remains in the plant is actually an alkaline material. So just normal growth of a plant will take up cations, will excrete acid into the soil, and the plant itself will become alkaline. And in a natural cycle, that plant dies, returns back to the soil surface, the alkali in that plant goes back to the soil, and then the organic anion joins up with the hydrogen ion, and you've effectively consumed the acid that was created when the plant grew. And so that creates organic matter, which can then be broken down by microbes and turned back into carbon dioxide and water. And you can see that we started with carbon dioxide and water and we ended with carbon dioxide and water. And so that's the carbon cycle, and it's complete. And if that happens, then there should be no net change in pH. However, when it comes to agriculture, the whole thing is based on using that plant. And so when the acid is excreted into the plant, we remove acid excreted into the soil. We remove the plant by grazing, by cutting hay. The animal will consume it. It'll go into its meat, its wool, and then that alkali is then in the animal and will be exported when you sell it or the product. And so that means that the alkali is removing out of the paddock and leaving the acid in the soil. And so what doesn't happen is that microbial breakdown. And so when we build up organic matter, what we're actually doing is adding a source of potential acidity into the soil. And so where that organic anion plus the acid, that acid can come and go depending on the pH of the soil. So we've actually got a reserve of acidity in the soil if we accumulate organic matter. If the organic matter breaks down, that's fine, because that H plus is actually turning into water and disappearing off into the atmosphere. So we're ending that cycle. So basically, when we have agriculture, we remove alkaline product, and that's what's creating acidity in our soil. And of course, you can go further with that. The more product you remove, the more acidity you keep in the soil, because the more alkali you actually remove in your product. Now, when you look in soils, all those processes don't actually happen equally through the soil. They happen in different layers. And so got a picture here of a soil. You can clearly see the depth of it. You can see it's got a bit of organic matter there, mostly around the top 4 centimeters, because that's where plant material will decompose into. And so the alkali gets returned there. Now, when you look at pH, so this is pH and calcium chloride going from 4, which is quite acidic, up to 5.5, which is still acid, but most plants would be quite happy with that.
the pH is actually what we call stratified. So in the very surface couple of centimeters, the pH is quite high, because that's where that alkali organic material is getting deposited. And then underneath that, we have quite an acid layer, and down around 4.4, plants will not do well at that pH, and a lot of microbes won't either. And so this stratification is really common in pretty much all pastures. We also get it in cropping situations where organic matter is getting returned to the soil surface. So the alkali bit at the top is from that alkali return. The any acid excretion that came from that plant excreting acid as the plant grew tends to happen throughout the root zone. So a lot of that happens quite deeper down in the soil, not just the top couple of centimeters. And so you actually have these two processes which in theory cancel each other out to give you no pH change. We actually have them occurring in different layers in the soil. So the surface becomes more alkaline and below that becomes more acidic. Throw into that, so that's the carbon side of things. But we also know that nitrogen reactions that Jim was talking about, they happen at different layers as well. So that mineralization that consumes acid happens in the soil surface, like our alkali return reaction, and the nitrification happens a little bit lower down. And so that's a real big driver for that that decrease in pH in that subsoil, or when I say subsurface soil, like 5 or 6 centimeters down. And you think about a plant germinating, putting its roots through, it's got some pretty hostile pH to grow through there. So when you think of product removal, it's alkali removal. So if you're a great producer and you're producing a lot of product, you're removing a lot of alkali, and product removal, alkali removal, that's acidification. So there are no free lunches. If you're taking alkali out of the paddock, you've got to balance that system somehow by bringing alkali back in. Over to you, Jim.
Well, and this table that we've just clipped out of the New South Wales Ag Fact on soil acidity and liming, I might add, it is still probably one of the best little documents going around around the whole issue. Just tells you how much lime would be required for every ton of those different types of produce removed from a field. So let's look down the bottom at lucerne hay. So for every ton of lucerne hay, you're removing so much alkali that would have to be it would have to be managed by putting 70 kilos of lime just to neutralize the alkali that you're removing from the fields. Okay, so this isn't on now. So far, what we've been talking about are ongoing processes. They're happening all the time. And it's not just removed from the field. We should say, and Jason did mention it, it's also the fact that that sheep will eat in one area and they will excrete in another. Now that means essentially that area where they excrete gets the alkali, but the acid gets left behind where they ate. So even within a field, therefore, we get this spatial variation in pH, which becomes also part of the difficulty. In fact, as somebody who soil samples a lot, I can tell you now, we never sample. We avoid as much as possible sampling in sheep camps. Usually we're sampling for phosphorus, and we get far too much there, and it wouldn't be indicative of the paddock. So anyway, more of that later. So if you looked at those three processes, again from that same ag fact, and you look, this is just very, very general. So of the things that cause acidification, right? Now this is some figures done for the southern tablelands of New South Wales under an annual type of pasture, so subclover and whatever else. So the leaching of nitrate nitrogen might account for around 50 to 70% of all acidity, build-up of organic matter 10 to 30%, and removal of product 10 to 30%. All right, different for a cropping pasture rotation, and I'm assuming in the pasture there is no addition of nitrogenous fertilizers, which we are avoiding for the rest of the talk. So all of this is ongoing, even after you lime, it's happening. So the question would be, well, you know, what were soils like before we started, and what is the impact of all of this combination of all these processes on pH? Well, thankfully, in the southern tablelands of New South Wales, which I'll concentrate on, not because I particularly like them, just because there's some good bits of data from them. In one particular study, we've got paddocks that were originally sampled in 52, 53 by Williams and, was it Donald? Yes.
C.H. Williams and Donald.
Donald, yeah, Donald and Williams. And then again in 1977, 78. They also did comparisons of so-called virgin, or if you like, you know, I would have thought they'd be soils under native pasture that had never been fertilised or sown to subclover. That's what I would have thought, compared to soils that had been under subclover and super. We're looking at two studies, actually, the Williams one, and then we'll look at another one by Bromfield in a similar vein. Here is the first one. Soil acidified to depth perhaps by 1.2 pH units. This is, unfortunately, this is pH in water. Again, just subtract about 0.8 from it if you want to get to something that's you're more familiar with in terms of calcium chloride. So in 32 years, have a look at that. The couple of the things that Jason's talking about are quite evident there. So there's the virgin soil to the, which is the dashed line, okay, going right down to 30, 40 centimeters, and over away from it at a much lower pH, you've got this stratification of pH that Jason was talking about, and then essentially you've got very low pH till about 25 centimeters, which is increasing in time. I must say that once you get this low pH in the surface, it actually moves down, all right? It doesn't just stay static. So the hydrogen ions, the acidity actually itself moves down the profile. Again, Keith, I have to rely on a very good scientist in this area, Keith Hellier. He wrote that at about pH 5, that process is accelerated. Can you understand that, Jason, or you shouldn't go into it?
Yeah, and the lower it gets,
the faster it moves. The lower it gets, the faster it moves. So the acidity problem on the surface is moving down the profile. And interestingly, thinking about the driving factors, the organic matter accumulation, the product removal, and the nitrogen cycle effects, you've got this good relationship really between the soil pH in 0 to 10 centimeters and how many years since the pasture has been established. And you look around there at 50 years, the soil pH has gone down by about a unit. So it's because all of these processes have been ongoing. Now, Bromfield did a similar sort of study that he published in 1983, I think. In this particular study, once again, you've got, but this time he's used different fields. He's got 8 different fields here. 2 so-called virgin fields, has never, again, as with the last example. You've got 3 fields that have been under pasture for 26 years and 3 fields that have been under pasture for 55 years. Now, once again, you can see, you can understand now the, and some of these, just to have a look down there at about 30 or 40 centimeters, 55 years has dropped the pH, admittedly again in water, but it's dropped the pH by more than 2 units. So that has, as we'll discover a little bit later, that has an enormous effect on pastures, all right? And it is not easy to correct. It's not quite a one-way street, but it's not easy to correct. So many of you will be aware also that as the soil, now this is the bit that's hard. So far we've just been talking about acidity. Now we're just going to go into that little area about in terms of the implication for plants, because soil acidity does 2 things that have massive implications for the productivity and persistence of pasture species. The first is that as the soil pH goes down, the concentration of what they call exchangeable aluminium, but can we call it soluble?
Plant available.
Plant available. That's a better. Thank you, Jason. You may be hideous, but you're very bright. Plant available aluminium increases markedly. So let's go back to have a look at. I've put the last slide up again, and this time in the slide to the right here, we've got exchangeable aluminium across the top, and we've got depth on the y-axis, and we're just looking at the profiles A, D, C, H, and G. So A has never had any fertilizer or subclover, and so the amount of exchangeable aluminium, the pH is very high, as you can see. The amount of exchangeable aluminium is very little, or available aluminium, if you like. Now, whereas for C and D, the two next curves, you can see that there is quite a big bulge, particularly 10 to 20 centimeters down the profile of exchangeable aluminium. And right over to the two fields that have been under pasture for 55 years, massive amounts of exchangeable aluminium, right? Now, we'll talk about how we normally gauge aluminium when we go through another study. Jason.
Yeah, so just whilst that slides up, just want to point out, if our standard practice at the moment is to take soil samples of a 0 to 10 centimetre depth, and they go off the lab and you get back your soil pH and your exchangeable aluminium concentrations in that sample sent. That sample, 0 to 10, is effectively an average of what you see there on the screen. So on the pH graph on the left, the most extreme left-hand curves, the circle, the black line, you know, you're at 5 at the top, but you're at 4.2 or 4.3 by the time you reach 10 centimeters down. So what you get back from the lab from your soil sample will be average of that curve within that layer. In a similar context, in the exchangeable aluminium, you know, you could have at 10 centimeters, you could have almost 1 unit there of exchangeable aluminium, but at the very surface, it's almost nothing. And so you get an average if you're 0 to 10 sampling. So my point is simply this: when you get your 0 to 10 samples, you're getting an average of the 0 to 10. And so we know the pH is stratified. We know the aluminium could be stratified. So if you're seeing problems with root growth from establishing pastures, that could be a reason. And only dividing up that 0 to 10 into smaller increments and testing for aluminium and pH will you find out what the effect is.
Actually, it even goes a bit further than that, because if you're thinking about some species, we'll get onto this later, that are very intolerant of acidity, by just doing a 0 to 10, right, you wouldn't know much about aluminium at all compared to what it is at depth. And so a species like lucerne, especially if you just surface lime, you might have quite high pH near the surface, but diabolical levels of aluminium at depth. So when we're talking to clients and saying, oh, we think, you know, perhaps you could put some lucerne in this paddock, we always sample down to about 60 centimeters before we're confident enough to say, yeah, particularly if it's a paddock we don't know anything about, before we're confident enough to actually go ahead with the recommendation. Okay, now, just because I said so, if mostly when you're talking about aluminium, it's usually expressed as the amount of aluminium as a percent of what's called the cation exchange capacity. And so when this was done for the previous graph that you just saw, let's just go over to the pasture that was 55 years old. So they are the two curves, G and H, two pastures that were 55-year-old. Have a look, those figures down there at 40 to 50% exchangeable aluminium from 10 centimeters down to 50 centimeters. They are very, very high, and there are very few species that would be able to perform well at such high levels of aluminium in the soil. All right, so I'll just leave that there for now.
But even there, Jim,
yep, thanks, Nate.
If we look at D at 5 to 10 centimeters is getting up to that magic number of 15.
Yep, and therefore is problematic. So just to underline the important point that the soil is highly variable and needs to be thoroughly explored before you make expensive decisions. Now the other one, which admittedly I don't know as much about, but it's the same sort of thing. As the pH decreases, the amount of manganese increases. Manganese is a little bit harder to understand in some ways than aluminium, but this is a typical, and manganese can really affect lucerne and a lot of other species. So this is a typical set of curves too. So again, it's the same soils that we're talking about before, but here's soil A, not that much manganese. Soil D, 26 years of pasture more, and much higher levels of manganese that have come out and because of the low soil pH are now available to the plant and cause problems. Okay, we better move on. So species now, You know, at the start I said it depends, you know, to lime or to lime not, you know, to lime or not to lime. Well, you know, the reason I say it depends is because it's even more difficult, because species and even varieties within species vary in their response to acidity. And typically the species cultivars are divided into groups over. Now I'm just using a simple thing that's available to everybody on the net from New South Wales DPI. And you'll see that in a moment. But the key question when considering lime is, what species do I have? I mean, if I have extremely tolerant species, is it a sensible decision to make? If I have, if I'm setting up a paddock for a sensitive species, then I've got, and it's acid, at least in the surface, then I have to lime. Otherwise, I'm just throwing away money. Sensitivity is usually in terms of what we call sensitivity is usually in terms of growth impairment of the shoots and or the roots. It's rarely expressed in terms of persistence, which for many of you and certainly for me is a key performance indicator of a pasture. So if it doesn't persist, that's extremely important, has very, very big economic implications. But the problem here is there's not as much data available because it's much harder to get. So here's the aluminium sensitivity of some pasture species. Again, you'll see it's expressed here as a percent of the effective of the cation exchange capacity. So amongst those highly sensitive species, you know, you have your basically just about all the members, almost all of the members of the genus Medicago, so the barrel and strand and Burmetics, lucerne, and then a few other species as well. You go then through, so at 5% you'll expect some growth, some problem for those species. At 10%, some species will be affected. I'll make another comment about Phalaris later, because there's Phalaris and Phalaris, and not all Phalaris are actually that sensitive. At 15, those that could tolerate 15% aluminium, tall fescue, ryegrasses, high for white clover, and subclover. And then there's the highly tolerant species like the Cerridellas, cocksfoot and consul lovegrass, and a few others, and particularly Microlenus stipoides, weeping grass, that is extremely acid tolerant. Likewise, you can do, there are differences in tolerances to manganese, and so you've, again, the highly sensitive species, lucerne, barrel and Burmetics, can only tolerate much lower levels of manganese, and then up we go into highly tolerant species, which includes most pasture grasses. Right, but even sensitivity to acidity, you've got to think a little bit about genetic improvements too. So CSIRO, really it's Richard Colviner's work, you know, breeding, and Rex Sorum, I suppose, in the past, but breeding Landmaster and Advanced AT Phalaris. I mean, in some studies done earlier in this decade, they've performed better than cocksfoot, right? And this has led to a change in current recommendations in southern New South Wales. So even on an acid soil now, you probably, in most situations, you're probably looking at a species, cultivar of Phalaris like Advanced AT, because it was bred specifically for aluminium tolerance.
That's sensitivity to aluminium.
Yes.
For the pastures, the legume pastures, that's plant, not necessarily rhizobia.
So yeah, that's true. I mean, there's a whole, yeah, okay. So what Jason's talking about is these are plant sensitivities. When you're thinking about legumes, we know that legumes have a relationship with a bacterium in the soil called rhizobia, and that symbiotic relationship produces fixed nitrogen for free, if you like, from the air. It happens to soil acidity, all right, is problematic for those free living rhizobia in the soil, and affects the nitrogen fixation process as well. So it's not just the plant, if you like, it's the plant production system that's affected. Excellent, here we go. Now, if we look to acidity and pastured productivity, well, who would have thought? I've said again, well, it depends. It depends on the species tolerance levels and the levels of aluminium and manganese. Some of the processes affected are root proliferation. Jason's made some comments about that. And, you know, if the roots can't grow through that really high aluminium layer, right, then basically they can't get at the water that could be stored in there. All right, so and you know, it's a very, I'll give you a classic common thing that would have happened years ago. Somebody who had acid depth in their soil, so they plant some lucerne, and the lucerne would look great until the water started running out in late spring, and then the lucerne would die. Why? Because it couldn't get its roots through the really, before it was just, you know, earlier on in the season, it's just living off current rainfall. And then as that all dries up and the season progresses, it's trying, it can't put its roots deeper into the soil where the water is, bang, it fails to persist. All right, nitrogen fixation, we've just quickly talked about that. Even disease tolerance is known to have some interaction with what do we call it? With soil acidity. Ultimately, growth, competition, and yield are affected, which influences carrying capacity. Another way of gauging some of that is because of the differential effects on species of acidity, you get impacts on botanical composition of the pasture, maybe less clover, more grasses, whatever. And of course, that is their effect on persistence, but we'll be looking at that later. So just on the acidification side, and I know we've gone a long way, we've talked about this for a long time, but essentially the summary is in pasture production systems in Southern Australia, please remember that soils acidify. You do not fix acidity with lime, you manage it. Your soils are always acidifying, and if you're running a productive system, well, I think I've got it next. The rate of acidification depends on many factors, but would be higher in more productive pastures, all things being equal. You know, soil type, blah, 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 rainfall, blah, blah, blah. So it's important to note that. I thought there was a view around maybe some decades ago, but, oh, I've got low pH, I'll fix it with lime, I can walk away. No, 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 no. We know a lot more. We've gained a lot of knowledge over the last 40 years, which lead us to appreciate the fact that soil acidification is ongoing and needs to be managed. It varies in time and space. Jason's done a great job telling us about up and down the profile, and we've talked a little bit about removal of product from redistribution of product from one part of the paddock to another. Thank you very much. Species vary in their response to increased levels of aluminium and manganese found in low pH soils, and so you could probably expect variability in pasture response to lime. You'd have to expect it, and that's where I think we're going, hopefully. Now, not quite, we'll be there in a sec. So if we're liming to manage soil acidity, there are some fairly key questions. There are a number of products, lime, dolomite, burnt lime. Please note, I've put not gypsum again because I don't want that to, I don't want you going away thinking that either. For those of you who, look, the quality of lime is an issue that comes up time and time again, but really most lime that's sold should be sold with some indication of its neutralizing value. Pure calcium carbonate has a neutralizing value of 100%, and limes vary down to 60% really of the neutralizing value. So you have to make an adjustment in the calculation of how much lime you need based on its neutralizing value. I realize too, some of you are from areas of the country where lime is available, but sometimes at quite high levels of moisture content. Once again, that has to be taken into account when calculating the amount of lime needed. More on that in a moment. How much? Yes?
So when you get your truckload of lime turn up, if you haven't got a docket that says this is the average of the stack of lime that's come out of, then ring the company up and ask them for it, because it will mean the difference between 2.5 or 2.95 tonnes if you take the example there.
Thanks, mate. Thanks, Nath. And in the end, we'll talk about that too in terms of its impact. How much lime depends on the current pH, where you'd like to manage that pH to, and soil factors, particularly that cation exchange capacity, and depending on the calculation you're making, the exchangeable aluminium. Here comes Jason.
Yeah, just before we move on, the quality of lime, not only is it neutralizing value, but it's also particle size.
The speed of the reaction is due to particle size. Tell us more.
Well, and it's just that some people are tempted to purchase a lime that's cheaper, but the reason it's cheaper is because it hasn't been ground as fine as the more expensive product. Right. But it's a false economy because you're going to have to put more on of that
Will it
coarser
eventually?
lime.
Sorry, I'll ask him a question. Will it eventually react?
It's much slower, and so if it's 0.7 of a millimeter in diameter,
Yep.
your kids won't see it,
Oh,
right? So it's decades and decades. So when we say super fine, it's less than 250 micron in diameter. So it's go figure, super fine.
if my wife and I work out things well, my kids won't see anything. Anyway, all right. So there's a simple model that was derived by Hockman and a few others called originally called Limit. It's now what we've got down here is 4 different soils, and the predictive model is the black squares. The hollow squares are the results of an experiment where people have put on different amounts of lime and measured the soil pH. And you can see in 3 of the 4 cases, the predictive line is pretty close to what actually happened. You could almost write a book about the inability so far to actually totally nail the prediction of changing pH for an amount of lime. There's been 3 versions, for instance, of the Limit model itself. But once again, harking back to the soil acidity and liming ag fact, I only found out in a meeting with a whole lot of people from all over New South Wales and Victoria the other day that this thing is still used. This table that I've just put up is used by a lot of people to come to a decision about how much lime to put on. So what have we got here? Well, what we have here is the amount of lime, tonnes per hectare, assuming it's fine and has a neutralizing value of 95, to lift the pH of the topsoil to 5.2 from various current levels of pH, 4, 4.3, 4.7, and 5.2. And you'll see, of course, that the amount of lime needed increases with the cation exchange capacity. And of course, it increases with the amount of lift, the amount of, if you like, hydrogen ions you want to soak up. So the amount of lift in pH. Now, quite frankly, that'll get you in the ballpark. And it would be nice to have a perfect model working. I was told by one eminent soil scientist that is the holy grail, but I think we'll just leave it there.
And just before we move on, 5.2 is the target there for the the 3 left-hand columns, because at 5.2 you're basically reducing aluminium out of the equation. At 5.2 you will not have exchangeable aluminium, and that historically that used to be our target, but we've learned a little bit more since then, and hence that column on the right, which is the taking it up to 5.5, which Jim will talk about.
And there'll be more of that in just a moment. Now, in fact, not too far away. So now you would imagine there's been a lot of studies on the effect of liming on pasture growth of some sort, but the way in which the limes, but you would also imagine too, given all of the given what we've found out tonight, that there is enormous variation in, first of all, think of all the studies that have been, enormous variation in the starting pH, variation in the quality of lime, variation in the species in the pasture, all right? And there's also variation in the way the lime's applied. Sometimes it's been applied just top dressed onto the surface. Other times it's been applied to the surface and then worked in, and then a pasture has been sown over it. So surface versus incorporation of lime is something you've just, when you're reading studies and looking at results, always think, was it incorporated? Was it surface applied? Because if it's surface applied, basically the reactions take a lot longer. It's just as simple as that. So if you like, in a practical sense, your payback time is a lot longer. I dare say you all know that anyway. Surface liming, however, is more relevant to permanent pastures, and incorporation, like I said, leads to faster amelioration of pH, increasing of pH, and less stratification, less of that curve that Jason was talking about. I've said that already. Here's the trick. Let's go back and think a bit about those pH, pH curves at depth, after 50 years of pasture. You remember that they're very, very acid. So if you start putting lime on the surface, how long would it be until you made some impact on that really deep acid stuff? I mean, after all, do you really want to live with 40 or 50%, or your children or grandchildren want to live with 40 or 50% aluminium at depth? Well, the general answer, the qualitative answer is it's bloody slow. And I think one of the better experiments in this whole, I'm going to refer to it in about 5 or 6 slides tonight. One of the better experiments in this whole area was Master. And Master, the great thing about the Master experiment is it went for 17 years and it measured pasture and it measured, you know, livestock, and it had annual pastures plus or minus lime, perennial pastures plus or minus lime, so it was fantastic. One of their treatments was to maintain, or sorry, their liming treatment was to maintain pH at around 5.5, and they did that. They put on 7.9 tons. Now this, you know, this soil was about 4.2 or 4.1 when they started, but they put on 7.9 tons over 17 years, and this was the effect. So this is what happened in the surface pH. In the surface pH, they put on, there they are at 4. They put on their 3.7 tons. Now this was incorporated at the start of the experiment, and for the rest of the experiment they tried to keep pH at around 5.5. That's the lime treatment. The unlimed treatment stays at 7. But here's the interesting thing. Oh, and after each, I'll just go back, after each of these liming events, they've done a special sort of analysis. Regardless of treatments, PP is perennial pasture plus lime, AP is annual pasture plus lime. Forget about the other two. They're all going down at the same rate. Here is the soil pH at 10 centimetres, and down the bottom is the years from liming. It's just a straight line dive. Once again, acidification is always happening. But here's the interesting bit. Acidification is always happening in the surface, that's true, and we're correcting it with lime. But down the bottom, have a look at the hollow circles. They're fantastic. They are, that's the pH at 15 to 20 centimetres, and that has been in the treatment, right? In the treatment that has been limed, they've been increasing at a rate of around 0.044 pH units per year. So after 17 years, you've ameliorated or increased the pH by about 0.7 of a unit down there, all right? So it's part of the long game. If you're liming and you're thinking about the long game, you can make an influence if you're keeping that pH in the surface soil at a you know, comparatively high level in the 5.2s to 5.5s. You'll notice also commensurately the limes go, the pH is going up. The black circles is the exchangeable aluminium going down. Have a look at that. Exchangeable aluminium started at 40%. You've got it down in 17 years by liming. You've got it down to a manageable 5 to 10%. Jason's going to say something. We better quick hurrying with keeping people up.
So just back to that graph. Like, so that increase or drop of acidity at depth that Jim just showed you and the effect on aluminium, that was only made possible because the pH was kept up around 5.5. Now to do that took one big dump of lime of 3.7 tons initially, and then, if you like, some maintenance rates that were much lower, 2.6, 1.6. And so if you're not going to commit to that 5.5, if you were liming to just 5.2 to get rid of aluminium, you'd still have to do those maintenance rates, but you wouldn't be getting that benefit of ameliorating acidity at depth. So that one-off cost initially got you a long-term benefit. That's the thing that got you a long-term benefit, hitting that pH of 5.5 in that one major liming event.
Right, now because I'm naughty and I'm taking too much time, I'm actually going to skip the next few slides and we're going to talk about the rest of the master experiment, because I think it illustrates pretty much the effect liming can have on the system. So just excuse me, because I don't want to keep you up, but we could come back and see some of this stuff later if you really want. Okay, so master, as I said, long-term experiment. There's grazing as well as cropping, rotations between grazing systems and cropping systems. We're not interested in them. The main thing is here is the plus minus lime effect on perennial and annual pastures. Lime was incorporated initially, then top dressed. I've said that, and we've got a whole lot of key results to show you. Now, this first one is the pasture response. Now, this is actually pasture measured. I can't explain why today, not enough time, but it's only measured for a third of the year, all right? So really the differences between the limed treatment and the unlimed treatment for permanent pasture and annual pasture, etc., are actually 3 times this amount that you're looking over here. Now you can see usually they're positive, right? They're positive. And the funny thing about them is they're not usually significant, statistically significant. However, more on that a little bit later. But liming generally had a positive influence. The overall contrast, liming generally had a positive influence on, and a significant influence on the amount of dry matter. The key results from the bit now, liming also, because of that differential sensitivity of species, liming also had a big effect on the amount of phalaris. So there was more phalaris, there's a higher percentage phalaris on limed plots, and the basal cover was higher on limed plots. Subclover was higher in annual pastures, but not perennial pastures. Ryegrass was stable in perennial pastures and annual pastures without lime. It was reduced, that should say perennial, oh no, reduced in annual with lime. Now, interestingly, silvergrass increased in annual pastures and perennial pastures without lime, but it was less than 15% in annual pastures and lime, and less than 5% in perennial pastures with lime. Barleygrass increases in lime treatment to make up, if you like, for some of that decrease in silvergrass, but they were less than 3%. Barleygrass is less than 3% in unlimed. But then again, barley's sensitive to, barleygrass is sensitive to pH. Here is the basal cover of phalaris plus or minus lime. So the top line, if you like, through time is the decrease in the basal area of phalaris. The dotted line down the bottom is the rather unimpressive amount of phalaris that was found, the base of phalaris that was found in unlimed treatments. Now, master and livestock production, I'm only showing you this because in the end, right, in the end, you get all these pasture differences, they're significant, they're not significant, blah, 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 blah. But in the end, it's the animal. In these systems, it's all about the animal. Now, these plots were grazed with wethers, and the idea was to keep the weight of the wethers on limed and unlimed plots as close together as possible, and let the stocking rate be the response. So if there's more feed, you put an animal on there, but not so many animals that the mob got smaller in size. So if you look at the graph quickly on your right, you'll see that the weights of the limed, that is the dark, the filled in circles, and the unlimed, which is the hollow circles, they're about similar. The differences are so negligible. On the left, however, is the differences in stocking rate. The dark bars up the top is the perennial pastures. The dark bars are the limed, and the open bars are the unlimed. Now, in annual and perennial pastures, there is no doubt the stocking rate was higher, and that was significant. As a result, production essentially was much higher. So here in this table, we've got perennial pastures minus lime, perennial pastures plus lime. You've got a lime effect on live weight gain of 62 kilos in perennial pastures and 76 kilos in the annual pastures. The 62 kilos represented a 27% increase. The 76 represented a 34% increase in the annual pastures. Likewise, wool per hectare, whereas wool per hectare was greater, right, in the limed pastures by 12.9 kilos in the perennial pastures, and greater in the annual pastures by 11.3 kilos, leading to 28 and 24% increases. So, frankly, that's worth something. Now, what is it worth? Well, look, quickly, the analysis that was done, I'm not entirely happy with. And it's a bit dated, you know, because have a look at, you know, the gross income per DSC, the gross margins per DSC. There's a few problems there very low gross margins per DSE. And so although an economic analysis was done, you know, with the amount of lime, was it worth it? Rah, 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 rah. It's pretty hard to actually, identify with given current situation. And why is that? Well, Dave Brown was lucky enough to give me some figures from the Holmes and Secker benchmarking. So for a prime lamb flock, the gross margin per DSE is $34 averaged over the last 5. For the average in the benchmarking group, it's $46 for the top 20%. Now, when you take that into account and the cost of putting on extra DSEs, right? And you use, so I've done a little analysis that shows the payback period at $100 to buy a DSE, at 5 years till we get our maximum increase in DSE, which would be the 24% increase in stocking rate that was achieved in master. And this is based on a 3-ton application of lime. And at the 35 type DSE with a 25% increase in stocking rate, so pretty much where master is, that's a sort of around a 9-year payback period. But if you actually are making $45 a DSE, so you're in the top 20%, that's about 8. If you actually then have a look at what those are in terms of internal rates of return, that is the interest rate you'd have to pay for the investment to be worth nothing, then it's still, look, it's still around 14 to 16% at $35 a DSE, rising to 17 to 20% at $45 a DSE. So for 3 tons of lime, you know, in that sort of using the sorts of data that you can get out of master, it's, I think, liming in that particular case, starting from a very low pH, is basically, it proves essentially that liming is worth it, straight out. Now, I haven't, is it profitable? Well, the question would be, well, that depends, because how profitable are you? At the top 20% end, liming with an internal rate of return of 20%, plus all the other effects that it could have, modifying the deeper pH, providing a better growth environment and better opportunities in the future. Well, yeah, I'm sure it's worth it, but it depends, doesn't it? Use of current prices, that's the average of the last 5 years, but if you use current prices, make it even more profitable, but then it would be a silly thing to do. Other benefits are difficult to quantify, like that longer persistence of pasture, reducing sowing costs, so I haven't done it. Just quickly, what else could you do about acidification? Well, whatever you do, the best, one thing for sure is to have a productive perennial pasture soaking up as much of that nitrate as possible so it doesn't leach to the bottom of the profile. That's one certain thing for sure. Maybe, I mean, if you're a person who cuts hay, I guess the idea would be to feed that hay back on the paddock that it was cut from, so you're returning that alkali that Jace was talking about earlier. When it comes down to it, however, all of these things are nice, but lime is the answer. The only real questions are how much and how often. Now, I just wanted to show you, lastly, I just want to show you this data from our clients, right? So check this out. You've got a property of 40 or 30 or 40 paddocks, and you've looked into this liming cape and you thought, gee, it might be worth me having a think about this. Well, the first thing you'd know is what the pH of your paddocks is, right? Now, these are box plots. And they each one of those box plots represents the variation in pH in paddocks. So so it's a single point for each paddock. So each one of those is a variation in pH in paddocks that of our client group.
On a property
on a
where
particular,
we've sampled more than 8 paddocks on that property.
So you can see the one I've got my mouse on at the moment. A pH, the bottom 10th centile, right? So 10% of values below this one, but it's at 4.25. I don't know why that keeps disappearing. And the top paddock's at 5.5. Right, now you can see the variation without explaining the box plot and stuff like that. The little line in the center of those boxes is the median paddock. Okay, so we've got massive variation there, but if you have a look at it, within most properties there's pretty big variation. So the first thing in the decision making process is to know where your pH is at, right? How to prioritize: first know the pH of your paddocks, Consider the botanical composition. Paddocks with low pH and useful populations of perennial species, I reckon, should probably be the target. So to lime or not to lime? In the end, Dave, I know we've gone too long. You probably want to kill us, but I still think the answer is it depends, and we probably need to discuss it. Over to you.
Thanks, Jim. Thanks, Nathan. And Jason, no worries, Jim. It was worth it, and it gave me the opportunity to grab another glass of wine, so thank you for that. We're going to give you guys a quick break now, just to have a rest there for a second. Now, look, everyone, thanks so much for sticking with us. We had always planned for Jim's presentation to be a little bit longer than usual because liming is a very deep and complex subject, and there was just no way we were going to do it justice and provide a rational answer this evening without going a little bit over time. So that's all good. Now, don't forget, if you are looking to hit the hay, don't forget to complete the post-webinar survey. It's going to pop up quickly if you exit the webinar or we shut it on you. We always value your thoughts and critical comments on it, and we pass them on to MLA and the presenters. Next week, we have Basil Doonan from Macquarie Franklin in Tasmania delivering on urea, or should I say nitrogen and gibberellic acid in pastures. And that's really shaping up to be another great webinar, as equally useful and relevant as tonight's webinar. And I think a very good continuation on this theme of boosting pasture production, which is becoming an increasing priority of producers in this high commodity price environment. Now, thanks for supporting the webinars and joining in. Don't forget that if you've got networks and friends and you like what you are seeing and hearing from the webinars, if you think they're useful and relevant, then please pass on the opportunity to them as well. Keep an eye on your on your email and your text messages, because I'll be updating you as we progress through the remaining webinars of this webinar series. There's plenty of questions coming in. Jim and the team there, Jason and Nathan. So I might take the liberty of kicking off the questions. Now I'm just going to play dumb, if I may, Jim. Now, is there any indication that the use of superphosphate fertilizers will increase the rate of acidification? And is that due to the extra production, or is it to do with some chemical, the actual super creating a chemical imbalance?
Well, I really hate it when somebody who's asked a question says, great question. But anyway, that's a great question. So what I'm going to say, Dave, is and the reason it's a great question is because it addresses a commonly held myth. Okay, so superphosphate directly does not acidify the soil, but indirectly through the increase in production, through the increase also not just production generally, but in particular of the legume component and all the impacts that has on the carbon and nitrogen cycles that we've been talking about a bit earlier in the talk. It's through those that you get that big acidification.
And
right,
Jim,
yeah.
Explain your differences between your annual and your perennial pasture for leaching nitrate.
Well, I mean, so some work was done by Anna Ridley down at and a few others down at Rutherglen years ago that demonstrated that you had higher levels of the nitrate leaching component under annual pastures, right? Simply because they didn't have the root structure there to capture as much nitrate as the perennial pastures have early on in the season, all right? Well, that's mainly the right, and particularly over the winter. So if you've got, in the old days when they just did sub and super, what would happen is they had this, they put in super, they might fly some sub on and stuff like that, and then a native pasture would get overgrazed. Most of the natives would die out. You'd end up with largely functionally an annual pasture, right? The superphosphate basically had driven a system into annualization and into high levels of nitrogen fixation, much higher levels of production than had ever been seen. So the carbon and nitrogen cycles basically are turning, if you like, a lot faster, and therefore leading to a lot higher rates of acidification. Good question. Thank you very much.
All right, Jim. Thank you. Question here from Frank. Thanks, Frank. Frank's from the northern end of the Monero. They're on granite acid soils, which go all the way to China. Frank suggests that unless you're in a livestock situation, you are ploughing and seeding, fertilizing every year in the hope that it will rain at the right time. And then why would you use lime? Frank's system is based on a deep-rooted perennial pastures, so that liming seems to be of little value. What does the panel think?
Well, if I've got the question right, I think all productive systems, or the best productive systems, are based on deep-rooted perennial species. But where does the nitrogen come from? Well, the nitrogen comes from the legume component, and so in a system that's very, very highly acidic, that compromises the legume performance. So I would think that there would still be room, I would have thought, for a positive response to higher pH by the legume component. If I don't know if I've got that question by the short, if I've got that question right. What do you blokes?
Yeah, I'd also go on to say, if we go back to what we were discussing earlier with the nitrogen fixation and the symbiotic relationship we have between the rhizobia and the plants, the legumes, that we know as the soil gets more acid, those rhizobia aren't as tolerant. So again, you're going to reduce productivity in the longer term in those pastures. So I think it's a matter of knowing your current situation, knowing a trajectory to where you want to be, and putting a plan in place to get there.
Yeah. Right. Thank you. Now that answers the question, and that's really good. So the question here from Neil, I think we may have touched on this, but you may want to just quickly summarise the absolute keyest points. Are all limes equal, or do some limes perform better than other limes?
Yeah, well, it depends. Well, there's two things to that. Jason will probably do this better than me, but no, not all limes are equal. So the neutralizing value is the thing in lime we will call calcium carbonate, right? So the thing in lime that tells us how effective it is at neutralizing acidity, Jason touched on it as well, is the fineness of the lime and the neutralizing value.
Yeah.
However, there are other liming products. Lime is a bit of an interesting term. There are other liming products which neutralize acidity at higher levels, kilo per kilo, than does lime. Burnt lime, dolomite. Dolomite does as well. So sort of double-barreled answer to that question, basically. But no, lime is not lime. And I also stress, only because I had some people that I talked to from southern Victoria telling me a few years ago that some of the lime they were buying was just basically dripping with water. So when we're talking about this, we're talking about how much lime is required, etc. It's assumed that that's dry. Okay, it's assumed that it's not. It hasn't got such ridiculous water, 20% worth of water or something like that. So that has to be taken into account as well. Just to make sure that we've got enough to do the job. Yeah,
right. No, thank you. That's great. Question here from Jan. Will aeration of the soil also help with raising the pH, especially if it is done at the time of spreading?
Oh, this is one for Jason.
So aeration, I guess you potentially, depending on the soil type, like how the texture and that, you just could be creating pores that may move lime particles through, given enough rainfall. But that would, if you've got a sandy soil, then lime can move through it a little bit faster than a clay soil, obviously. So aerating, it depends how you do that, I guess. But well, the other thing that aeration does is help break down your organic matter.
And then so that you'll get an increase in pH from that organic matter breakdown too, potentially. But certainly, cultivating incorporates that lime in, which gets you the biggest benefit that you're going to get.
Yeah, so what I'm taking away from that is that it's not so much about the aeration, it is a form of incorporation.
Yeah, indeed. Yep.
Okay, question here from Neil. Neil asks, is it true that manganese in excess can make the soil hard?
Yeah.
Blank faces.
I'm sorry, I don't know the answer to that.
No worries, moving on. Neil again, what percentage of calcium cations is desirable in a soil test?
This is one for Jason.
Yeah, there is no ideal percentage. The research shows that pretty clearly. I know there's a train of thought out there that says otherwise, but the research is pretty clear on it. And so basically, if you look at a calcium-magnesium ratio, if you're above 2, calcium-magnesium ratio above 2 and below 20, then you're in happy times. If you're below 2, then the soil structure deteriorates. So maybe that same question about the manganese, if that was talking about magnesium, high magnesium, exchangeable magnesium relative to calcium can make the soil hard or compacted and less desirable. And once you get over a calcium magnesium ratio of 20, that's when you start getting your grass tetany problems with your magnesium deficient pastures.
I should also add that I spoke to Mark Conyers a little bit about this one day and said, how often would we see a calcium deficiency in plants? And he said, well, never. Perhaps in apples and strawberries every so often. So it's extremely rare in Australia.
Yeah, you see it in horticultural crops where plants grow fast, and often the skin integrity is important for the product. Yeah.
Yeah. Well,
Dave, over to you.
Thank you. No, that's great. Is deep ripping a consideration? Do you think that's an economic consideration to let that quicker infiltration through the soil profile?
So we've got a GRDC funded project that does that. It's one of the treatments is basically ripping lime in, and I mean that's a pretty severe bit of engineering you got to do. It's quite expensive to do, and then you've got your physical disturbance as well. So in a lot of cases, deep ripping is just not an option. You run the risk of having some exposure issues to erosion. But we are testing that currently, and we'll be doing the yields and economics on that as well in a cropping context, because it's GRDC funded. But it'd be great to do some lime movement and more lime work in a permanent pasture environment for sure, if we got the funding.
No, perfect. No, well, it sounds like a call out to any funding bodies out there that are interested in this. Then talk to Jason. He'll be happy to hear from you. Now, this is a good probably comment / question from Campbell in regards to this particle size that Jason was talking of. That would mean that pelletized lime would not be a good option for pH correction due to the time it would take to have an effect.
The pelletized limes that I'm aware of are actually, some of them are actually fine lime that are just joined together with some form of coagulant, like some sort of binding agent. And the idea is that pelletization allows you to distribute it easily with on-farm equipment, no specialized equipment. And then once it hits the ground, the binding agent lets go, and you've got those fine particle lime particles in the soil. The issue I have with that is, one, it adds a cost to that, which may be greater than getting a contractor in to spread normal lime. And two, you've got that lime in a really concentrated area where the pellet dissolved, and you want to get as much soil in contact with those fine particle lime particles as much as possible. So again, a bit of work needs to be done on that. But if you were using pelletized lime through a seeder to ameliorate acidity at a certain depth within the root zone, for example, I can see it being beneficial there. But in terms of spreading on the surface, I think there's probably more economically effective ways of doing it.
Great, right. That's perfect. Thank you for that. So it sort of dispelled that issue for Campbell. A question here from Roan. Is not lime also used to alter the calcium-magnesium ratio as per the Albrecht teaching? It's not just about the pH of the soil. Comment on that?
Well, here we go.
Do you want to open this can of worms?
Well, I'll give it to Jason, but I can only recommend a really good article. It might be worth, I don't know if you can put up things that people can get, Dave, but a really good article by Kapicki and Menzies on the Albrecht system and the research that showed that it's not necessarily as scientific as some would suggest. But I'll let Jason speak to it more because it's more his bag.
Yeah, that paper Jim spoke about is really good because the great thing about it, it actually used some of Albrecht's data to show that the calcium-magnesium ratio, there is no actual ideal ratio, and their data actually shows that. A lot of times where people use that and they'll apply lime to, in inverted commas, correct the calcium-magnesium ratio, what they're in effect doing, because they're adding lime, they're increasing the pH and then giving all the credit to the calcium, which, as Jim started the talk, it's the carbonate in lime that does the job. And as we've described, like the response curve to adding calcium is pretty flat. So it's the carbonate that increases the pH, and it's the increase in pH that decreases the aluminium concentrations, which then gives you your increases in yield or production.
Great, that's perfect. Thank you, Jason. Good question here from James. How important is understanding the spatial variability of pH and therefore using variable rate technology to spread lime?
Well, I think there's great opportunities in doing that. What do we need, though, to do that? Well, I guess what we need is that we need the variability in pH to be in a pattern, right? So what I mean by that is, so what happens when some bodies go out and they measure pH across a field on a certain grid, right? They do a few pH measurements and they at a point, is that right, Jason? And they at that point they give a value to, and then they'll draw what's called a variogram essentially, and say, well, that's the pattern of pH in the paddock. But as Jason's just about to tell you, that the scales of variability over a metre are just as big as over about 500 metres. Jason.
Yeah, thanks, Jim. So
we should have had that up.
Yeah, so I would say it depends how that variability in pH is measured, and so there are all sorts of gear, equipment out there that can measure pH in multiple areas within a paddock on grids and in real-time machines or whatnot. If you're to, I would say, based on what I know about pH variability, the amount of variability in a metre is roughly the same as the amount of variability in 10 metres or 100 metres square. So it's a very variable thing, and part of that's because of the processes we spoke about and when they occur and how they occur. But if you are taking measurements spatially, then a point in a couple of hectares, you really, if you're using that one point to give you a representation of the pH in that couple of hectares, you're really throwing chance to the wind there, because it is such a variable thing that you're trying to measure. However, if you are saying, right, within this 1 hectare or 2 hectare grid, I'm going to take several pH measurements and bulk them and average them so I get a value for this hectare grid, and I'm going to do that across my paddock, and then using other factors that might be it might be topography, it might be soil type, it might be where you perceive different production to be, or better bits of pasture, worse bits of pasture, to zone those areas and then within that zone, using all the pH values from those different hectare grids and averaging them to get an average for your zone, what you've effectively done is got an average, which you can then lime to, that is representative of many, 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 many cores. And that's how you get an estimate that's closer to the true mean of the soil that you're trying to represent by that sample.
So, Jose, how many cores designate a sample?
Yep, so a good sample in terms of pH, we know from very basic, simple research, 25 to 30 cores gets you a very good approximate of the mean of the soil that was sampled, with small variability around that mean. And you can sample more, but you don't really get any greater accuracy.
So the take-home message out of that is, if you've got somebody that's doing some grid sampling and you ask them how many cores are you taking per grid, and the answer is less than 25 to 30, the answer is there's the gate, keep going out, because the answer isn't going to be representative for what we've got or what we need.
Yeah, you're going to get numbers that have a lot of variability around them. You'll get a number, but how confident can you be in that number is the question.
Interesting. That's spot on. Thank you, guys. It's yeah, really it deals with the big issue around that variable rate application and the lime space, at least. Look, a good question here from Brad. Brad asks, what leaching takes place with lime if used on a floodplain?
What if used on a floodplain?
Yeah. So what leaching takes place?
Well, we're talking about leaching in two directions, aren't we? Really, we're talking about runoff. Are we talking about runoff and leaching?
Well, I'm not sure. But so leaching is good with lime, isn't it?
Well, yeah. So lime basically moves through the soil in water by mass movement. It doesn't dissolve as such. What happens is it moves with the water, particularly preferentially down bigger pores in the soil. But I would imagine if we're talking about in flood irrigation, if we're talking about potential runoff, we could lose some, Jason. I'm not sure.
Yeah, it depends. It depends so much on your ground cover and speed of water movement, all that sort of stuff. That would be, very difficult to answer a question on that.
Yeah.
But in terms of vertical movement down, floodplains are variable in their texture, and so you can get sandy soils closer to the water source, closer to the river or the creek, whatever it is. And in theory, yes, you'll get movement of lime a little bit better through that sand. It's still pretty slow though. And if it was clay, it'd be slow, really slow. Yeah.
Okay, great. A question here from Maxwell. Max asks, do the new release of fine-leaved cocksfoots have either a better production than, say, A.T. folaris, or are they more acid tolerant?
There's been some recent work. By Richard Hayes. Is he talking? I'm really not sure about the cocksfoots he's talking about because I don't deal with them much. But in general, AT was as good as, in that work I remember, AT was as good as most of the cocksfoots. All right, so including uplands, Curry, Porto, the old favourites. But I don't know about any others. I'd have to go back to the original work, but I'm not sure about any of the others in terms of their acid tolerance. I just know that it's sort of funny, but speaking to Richard Hayes over the years, he used to be a sort of cocksfoot fan, and then got the results from his masters and other work that he'd done, and he sort of turned his recommendation around because it was clear that Landmaster and AT were doing just as well and were probably more productive. But I'm sorry, I can't really help Maxwell with a blow-by-blow on cultivars.
No, that's fine. Thanks, Jim. Charles, good to see Charles back with us tonight and asking the good questions as always. Given the advances in plant breeding, i.e. the tolerance to acidity, and that pH seems to be stabilised at a low rate, is there any merit in just changing your plant species sown rather than liming? i.e. putting rye and cocksfoot instead of more sensitive species?
Yeah, well, I think there are, but the genetic gains are pretty slow in terms of, so, you know, so Dave, I'll just talk to you for a sec about this. So are we asking, should we not just bother with any of this stuff and just sow more tolerant species? Is that what we're saying? Is that the proposition?
That's the premise of the question.
Well, I think, see, then the problem with that is, then, well, there's a few problems. There's a few problems with that. Acidification, as we've already seen tonight, will just keep happening, right? And so probably down to, Jason, we're about 3.8 to 4-ish, around where it halts up a bit. But think about a pasture as a community of plants, right? A community of species. It's not just the perennial species. You'd want to be thinking about, I still think I think it's like Bill Clinton, like, it's the clover, stupid. You know, it's the nitrogen, stupid. That's what I always say to myself. It's the nitrogen we've got to be thinking about, because the nitrogen is the engine in our production system. And if we're not producing the nitrogen through the legume, right, we are just working at lower margins. So I would say, yeah, I guess you could think if we lined up all the species you'd want to be really, really acid tolerant, yeah, there might be a point there. But there is another point though. What if in trying to do that, you just let the acidification happen, and then you become like those pastures after 55 years, you've got 40% aluminium at depth or whatever, then your opportunity to grow perhaps one day a more useful species, in brackets, Jim Virgona always says lucerne, a more useful species then is basically totally diminished. I might say, interestingly, about the master experiment, after the third liming, it's a properly phased experiment. I don't want to go into it, but they re-established some of the pastures, and after the third liming, they were even getting persistence. Imagine this, they were even getting some persistence out of lucerne, right? That's how much things had changed. They turned a totally you know, a soil that was absolutely hostile to lucerne into a soil that, yeah, it couldn't maintain a big population, but it maintained a few. So I would say there are two schools of thought about this, promoting acid tolerant species as the answer. One school says, yeah, great idea, genetic gain, etc., etc. Another school says, well, you know, you want to look at the whole system and whether that's what you want. And I tend to be more in the second school, I think.
No, great. Now, there's a few things to consider there, but a good question and some very relevant points made on the answers. Question here from Graham. This will be a quick one for maybe Nath or yourself. Given the organic matter content of the top few centimetres of soil, are we better removing the top 2 centimetres of soil before soil sampling? It's from Graham.
Well, I mean, I've got the soil scientist now, he's scratching his beard, but I'll let him scratch his beard for a sec. I think the problem with that would be that all of our soil sampling techniques are based on, are sort of related to a standard procedure. So if we start doing something different now, for instance, if you think about what Jason was saying earlier about the stratification, we're going to remove the most alkaline bit, right? So now it would mean that all your values would decline precipitously from what they've been historically. And so it would tend to suggest, so that would be a stepwise change, and you'd be out of step with what everybody was doing. I don't know, Jason. It doesn't sound right to me.
I'm for it.
Oh, he's for it.
I reckon it depends what you're looking for, and it depends what you do with that test. Yeah. So if you're comparing that test to you know, response curves from experiments that look at the 0 to 10, then you must take a 0 to 10 sample. So you're comparing an apple with an apple. But if you're looking at, well, pH, and do I have an acid problem? Do I have an aluminium problem? Then in a permanent pasture situation where you're not going, there is no cultivation,
then I can see why you'd do it.
So what about the implications then, Jace, if we start taking that top 2 centimetres off for Coldwell P and sulphur and other things?
Yep, so that comes back to what you're comparing that value to.
Yeah.
So if you're comparing it to well, I can tell you in cropping, because that's what I have more to do with, but that number is used on a response curve that is for 0 to 10, and historically was well mixed in all the trials that were done in the 60s and 70s.
Yep.
That actually doesn't relate terribly well to what we have in the paddocks now. So I actually think there's quite a lot of, it's not new science, it's just we need to go and get our heads around what we're actually measuring, how the stratification nutrients have changed.
Should we be measuring within the 0 to, should we not ditch the top one, but should we just be measuring within the 0 to 10 more?
Well, I think so. Like that graph I showed of stratification, you only know it's there because in that particular case, I sampled it in 2 centimetre intervals. I'm not saying commercially.
That's right.
But not to 5 to 10.
Possible.
That's doable.
Well, I've done that for clients. I might also say that if you go back through some of the old data, like, well, there's quite a bit of it actually, there were efforts to break the, even in work that's 30 years plus old now, there are efforts to break the profile down into 2 centimetre sections. That data's there. I don't know if we've helped your question.
Well, it's all going to come back to time and money. If you want to do it, someone will be able to do it. It's just, are you able to pay the cost for that someone to do it for you?
And just have a very clear idea of what you're going to do.
What you're after.
Yeah.
So there you go. I think the answer is it depends.
Do it.
I think Nathan. I think I was right. Nathan's got the practical answer there. If you want to pay for it, you can get it. But whether the benefits there is another thing. So, quick question here from Lisa. Good to see Lisa online tonight. The best performing paddocks. Well, this is actually quite a long-winded answer. So stick with us. It's got some basic principles behind it though. The best performing paddocks often have a number of things going for them: depth, fertility, etc., and their product removal can be higher. So if these have become seriously acidic, do you recommend your clients lime these best paddocks first, or do you tackle the most acidic and perhaps the weediest paddocks first because they have the most to lose if not managed and the most to gain once they are limed?
Well, I'm not sure about the most to lose, the most to gain. I think the way we do it, or the way I think about it, usually would be, I'm always thinking, Dave, about persistence, right? So what I really want to do is, if I've got a paddock that has, new client or something, a paddock that's very, very acid, but it's still got a workable, don't ask me to define that, please. That's another talk. A workable population of Phalaris that's worth, might have declined a bit, but there's still some there. Then I would, and the pH was low, I'd be working on a paddock like that rather than a paddock that was really, really weedy and had hardly any in it, right? So I would always be thinking about 2 things. The potential productivity of the paddock, the state of the pasture in that paddock, and of course the current pH. All right, I think you have more to lose in a pasture that by basically saving a pasture from becoming a basket case than you have to from liming a pasture that already has become a basket case. There you go. I thought I'd get there eventually. Jason looks like he wants to say something.
I'm glad it's a good question. I'm glad it came up, because the other thing, like we're just talking about measuring the pH in the 0 to 10 centimetres. There's a lot of soil below that, ideally, right? And your liming's going to address that acidity in the surface soil. So we need to look at, well, okay, if we fix that, what's the next limitation? So if you've got a shallow soil, or if the acidity goes down 30 centimetres, 40 centimetres, then that liming in the surface is going to have a minimal benefit because you've still got a limitation there. So in addressing that, I understand what Jim's saying and I agree with that, but I'd also say when you're going to lime a paddock, we need to dig down and actually see what other limitations exist for the plants that you're going to grow. If I lime the surface and I fix that acidity higher up,
what's the next limitation to good growth, and you know, that also tells you how valuable that liming is.
Perfect. Thanks, guys. Now, really good, really good. Now, another question from Maxwell here. Can acidification be ameliorated by building up soil organic matter?
No. No.
No.
No.
Just increases the amount of reserve acidity.
Yeah, you're creating a store of acidity. So, yeah, you've given somewhere for the hydrogen ions to hang out and then eventually come back into solution as they can do, and drop the pH. So, if you want to increase pH, you need that organic matter to break down, which is not an accumulation. You need it to be decomposed.
Yeah.
But Jace, we're always being told that we need to have
Increased organic matter.
Increased organic matter in our soils.
Yeah.
So because it has other positive benefits.
And it does, and so it stores moisture, and it's a store of nutrients, and increases CEC, and that's great. But work that was co-authored, Mark Conyers was senior author, but clearly showed that to increase organic carbon in soil, one of the consequences of that is to decrease pH. Like, to actually get more carbon in the soil, the consequence will be an acidification of that soil.
So sadly, we go back to the Rolling Stones principle of you can't always get what you want. Jagger and Richards, 1970.
Okay. Maxwell's he's asked a few questions this evening. Thanks, Maxwell. When does nitrogen become released into the system by the breakdown of legumes? And what pastures are best suited in these southern pasture systems to best utilise the nitrogen at that time?
Well, I'll do the when bit first. It is to a degree the breakdown, which is microbially mediated. So moist, it needs temperature and it needs moisture. All right. So you can imagine in really hot, dry summers, not much is going on. Right. Really cold, even in cold, wet winters, not much is going on. So when the temperature and the moisture content of the soil are favourable, then that stuff is being broken down. Now, part two of the question was what again, Dave?
What pastures?
Okay, so what pastures are? Well, the end of that is it goes down to saying, well, the
perennial.
Really, it's got to do with perennials essentially. I remember doing some research work back years ago in the cropping zone of southern New South Wales. So let's just go back to that. Before I say that, let's go back to the nitrogen cycle and say, well, what happens when that stuff breaks down? Essentially, you get an accumulation of nitrate in the soil. If it gets picked up where it accumulates, that is essentially a neutral set of reactions, all right? There won't be acid added to the system per se. If, however, it leaches, then you'll either get one of two things happening. You'll either get acidity in the surface and, to some extent, that be a neutralization reaction, if you like, at depth, or if it leaches below the root zone, it just leaves the acid behind. Now, so what would be best to combat that? The only thing that we found, well, the only thing that I can think of, and there's been a bit of research to support it, is making sure the pasture has perennial species in it. Now, I know that would be like, you know, telling your grandmother to suck eggs for a lot of people here, although these days grandmothers have teeth, so it's probably doesn't mean much really, but anyway, it's an old one. But I realise that a lot of listeners know that. Okay, now essentially, beyond having a perennial there, perennials, it really depends. Like, I could say to you something trite like, well, a perennial that's really active over summer would be better, etc., etc. But then we get into a whole area of, does the environment allow that to persist? And so I don't want to give a trite response to that. So all I'm going to say is perenniality, is really important. When we did our research work in the southern slopes of New South Wales, admittedly in the cropping zone part, where we had perennials, we got very, very little of that nitrate leaching down the profile. But that's under lower rainfall conditions than many of the listeners. And so you can have perennials there. That's the best thing you can do. I don't think you can do much beyond that.
Perfect. Thanks, Jim. No, that's great. That's great. Now, got some really good feedback coming. I think there's a few people, just one or two, departing for the evening, but they're thanking you. Great speakers, great subject, and very positive sentiments there. So thank you to them. Should we be considering soil EC or electrical conductivity, I think, when determining aluminium toxicity levels? From Ben.
It depends how you measure your aluminium now. This goes chemically a bit beyond me, unfortunately, but I know you do when aluminium, so it's not the percent exchangeable aluminium, it's
saturated?
No, it's the the answer is yes. The best thing to do is we use exchangeable aluminium, right, as a percent of cation exchange, and the answer to that is no, you don't need to. But if you use another extraction, I think it's the calcium chloride extraction of aluminium, then the answer is yes, I believe. Now, the best thing to do there is go to New South Wales DPI's website and download that 2005 Ag Fact. There's a nice little table there which outlines exactly what Ben's after. Sorry, I can't remember it off by heart, but yeah. So the answer is depends how your aluminium is being measured.
Perfect. No, that's fine. Thank you. Look, a very practical question, and thank you, Melanie, for this. Would it be better to lime less often with large doses or more often with lower dosages? Or here's a crack at you, Jim. Don't take it personally, but does it depend?
Yeah. Oh, look. Well, Melanie, it depends. I actually think, to some ways, look, I think we'll throw to Jason on this one, but I think there's an economic thing here too with respect to the cost of spreading, right? But that's pretty, obviously. Putting lime out let's think about this. Putting lime out every year would be a pretty dumb thing to do, because you have the cost of spreading every year. You'd be putting out, I don't know, what are we acidifying out? Let's just say we're acidifying it in a 10 years. Let's say in a really productive system, you might be acidifying at the equivalent of 250 kilos of lime per annum per hectare, right? So doing that every year would be pretty dumb, because you're racking up yourself a pretty large spreading cost. However, it's something I've wondered about a fair bit. The habit seems to be, say in southern New South Wales and permanent pastures, the habit seems to be, well, what we do is we lime, we bring up the pH, and then we let it get down to sort of pretty low levels again, and then we lime it up again with another 2.5 or 3 ton, right? And we keep on sort of riding that sort of wave. There's no real measure there of the loss in production that you get from going down. So I don't think I can answer the question in a quantitative sense, because I don't think the work's been done. But Jason's scratching his beard again. We'll go over to Jason.
That's a straight out lie.
He is.
To me, to answer the question, I just come back to the graph. It was one of the master graphs, master trial graphs that showed the pH with liming, and it looked like a sawtooth, like and so that big one hit of lime initially of 3.9 tons, whatever it was, and then after that, smaller maintenance rates. And so the research shows you have that first initial one-off big hit of lime to get you up over that 5.5 5.5. That's the key. We know the research is really clear. Once you get up over that, you've got more chance of getting alkali moving down into the profile. Once you're up there, your maintenance rates to keep it up there are effectively very similar to what the maintenance rate would be if you were picking a lower target. So all you're really committing to is to a larger initial liming event. And then after that, the question how often and by how much really comes down to how expensive it is to spread and how difficult it is to get smallish quantities of lime in. So, and the other key part of that is knowing what the pH is in the paddock that you're working in for, as the years go by. So you can actually monitor the decline in pH, so you know when you're dropping to a level that requires liming again. And again, the target is keep that pH up over 5.5 would be the ideal. So annual soil testing would be a key part of that strategy to do that. But one-off initial large makes a lot of sense.
Look, I might just ask a question of you there, Jason, or the team. For the benefit of the audience this evening, that first lime application of 3.7 tonnes per hectare was incorporated. Could you give us an indication, even a very cursory one, of the number of years, what would that line have looked like had it not been incorporated?
Yeah, so the problem is 0 to 10 soil sampling. If you've got a large quantity of lime sitting on the surface, and because lime doesn't dissolve, if your pH is around 7, the lime's not dissolving. It'll be there, but it's not dissolving. And so if you sample that undissolved lime in your 0 to 10 and then mix it with the rest of the soil and stick it in a test tube and measure the pH, then it will react. And so you actually get a false measurement. I know where you're going with that question, and we need to do a lot more work in this, because what we know is the movement of that lime from a surface application non-incorporated, the movement of that lime, organic matter actually plays a big role in that. So the current pH that you're at, the organic matter amount and quality has a big impact on the rate of alkali movement through the profile. And from what I know, we don't know enough about it, and we need to do more.
Okay.
I understand the question, and we need an answer for it.
Yeah, no, great. No, that's fine. Okay, let us and just one more thing. So if I was to clarify, so the reason why we're aiming for 5.5 pH and not say 5 or 5.2 is that it's not to do with the aluminium in the top, the reduction of exchangeable aluminium in the top 10 centimeters. It's to do with the raising of pH levels at depth. So is that am I interpreting that correctly?
No, that's spot on. It's all about getting a result below the depth of incorporation or the depth of placement.
Okay, perfect. No, thank you. That clears things up for me, and I hope it does for the audience as well. Okay, good question.
Dave, hang on. Dave, have you still got my screen?
Yeah, we're looking at everything you're doing.
Good.
He's
just
trying
hang
to
on.
get something up for you to discuss.
Okay. Look, this is for all those who have hung on, I just have to show you this. This is the most magnificent thing that I've got up on the screen. Can you see that picture that I've just put up?
You can. Yep. That's great.
Okay, so I just want to explain what that is. This is just fantastic. So this is at Charles Sturt University. You'll see where my mouse arrow is at the moment. That great big long plot, if you like to see, it's about a hectare in size. It is a lucerne, okay? It's a little lucerne pasture that's used for the students. So we've got a sort of resource of different types of pastures and crops near the school at CSU. That's fine. But have a look. You see those little dark bars down the bottom? You see those 5 dark bars down the bottom? Yeah? Dave, you see them?
Yes.
You've got to say yes. Yeah, cool. Okay, so you know what they are? Now these plots basically got established in the last few years, right?
Lucerne got established in the
last few years. The Lucerne got established in the last few years. Those dark bars are lime plots from the 1980s. That's the difference, even through today, right? That the lime is making at some, one would imagine, at some depth in the soil. I'm not joking, it's the 1980s that lime was put out. I don't know what rates, I don't know what dates, I don't care, right? It's just and when you walk across those plots, it's not only from the air that it stands out, you know you're somewhere a bit different. Now that is the difference, and I haven't talked enough tonight about playing the long game, but for the listeners who are still left here, and they are playing the long game, let me tell you, it's late, but for the listeners who are still left here, lime is yep, we've given you the economics and all that sort of stuff, but it's also a long game, and the implications are positive. You know, the implications are very positive.
And that image is just a Google Earth image, and that was during the drought. And so my add-on to what Jim just said is, we saw that effect because those lucerne plants are clearly getting moisture lower down. They're able to get their roots through a hostile soil and lower down. And so you're getting that effect was more obvious in the drought than a good year. You don't see those stripes in a good year. And so you're getting the benefit from that lime in the years where you really need it.
Yeah, and Jason's made a great point there. Sorry, folks who've got more questions to come, but Jason's great point there is, you know, most economic analyses aren't penetrating enough to take that into account. That'd be, I mean, a good one should be, but most aren't, usually because the data's not there anyway. Sorry, Dave, there's probably more questions. Sorry about that. I just had to rave.
No, that's good. No, so that's actually a very interesting picture, and I think everyone will be quite interested to see that. Now, there are a fair few more questions to come. They're all great questions.
We've only got half a glass of wine each left, so you better hurry. Yeah, let's go.
Is sowing lime pastures seed worthwhile? From Bernie.
Is sowing
pasture-coated, lime-coated pasture?
Yes, it is. This could almost get me into my favourite rave, and that's pasture coated seed, pre-inoculated coated seed, but we won't go there. The answer is if it's well done, then we provide a more favourable environment for the rhizobia legume association that's going to fix all that nitrogen for us. So in and again, thinking about Jason's stratification thing, we're putting that lime on the top, but we're potentially putting that seed underneath there into a more acid part of the soil, which is spatially variable anyway. So yes, my answer would be, I think it still is recommended practice, and I think it's justifiable. Yes.
Okay, great, thank you. Okay, good question here from Matt. What's the panel's view on a farmer applying 1 tonne to the hectare of lime when the recommendation was for 3.5 tonnes per hectare? Should they even bother? Thanks, from Matt.
Well, Matt, it depends. Generally, I would be certainly look. He's going to, I shouldn't say he, could be she. The farmer will get some benefit. The farmer will get some benefit from the 1 tonne of lime. There will be a reaction that increases the pH. But if the recommendation has been sensibly arrived at, so, remember we said, what are we trying to achieve with lime? What's our pH at the moment? What's our target pH? What's our cation exchange capacity? So in other words, what's really happened is somebody's gone to the trouble of saying, well, you need to put on 3.5 tonnes because your target is 5 point whatever. And now now as a result, the farmer's only going to go from 4 point whatever to 4 point and a little bit more. So I would think that would be of only marginal benefit. Okay. We ought to go back to Jason's answer to the previous question about the great value and that big increase in pH, and then the money that needs to be spent after it. But we're not even going to get there, are we?
Okay. Question from Dwayne. What time? This is maybe already sort of covered this a bit, Jason. What time period would you expect surface lime application to a phalaris-based 15-year-old pasture? What time would you see an increase in pH and then productivity from a starting point of 4.8?
Yeah, I can't answer that question. I don't have data to answer that.
Well, I'm sort of at a starting point of 4.8 in calcium chloride. Man, I think it'd be very difficult to pick up much of an improvement. Let's just go back to the first part of the question, which was, I'm going to surface of apply lime. However, hang on, we actually ought to think about this. Let's go back to the way Jason answered an earlier question and think about the fact that, yes, we got our big increase in pH and then it started going down again, and now it's at 4.8. So if we don't lime, we know it's only going to acidify more. So we're really asking if we put, what are we trying to do, really? Do we think we're going to get, I can tell you now, if you think you're going to get a big increase in dry matter production, etc., from liming at 4.8, probably not going to occur. It's not going to be very large. But if we think we're going to get a big, if we're going to get advantage out of keeping the pH up in that 5.2 plus region, the answer would be, I think if there will be, it depends on the soil type too, but there will be advantage in doing that. And the higher we keep that pH on the surface, the faster the lime moves down through the profile.
So it may I guess, to what I take from that answer is, it's maybe not a gain in production, it's a maintenance of production. So you're
correct.
You're stopping yourself from suffering a decline, a loss in production.
And you're also, depending on what the pH is at depth, you're also probably may well be having a positive influence down there.
But not just there. If you go back to the rhizobia issue,
if
the rhizobia don't tolerate pH below 5, and you're looking to increase nitrogen fixation by improving the rhizosphere so the rhizobia can fix more nitrogen, then yes, you may see a little increase. But again, I don't know if data out there to back up any of the claims.
Again, it's more in that one. It's more getting on that, like the master experiment, getting on that, getting on the train there and making sure that we keep on putting our lime out and managing the pH of the soil. But trying to ascribe an advantage to each application would be a bit, each particular application would be a bit difficult. I would say all I can say to Matt is this, right? Interestingly enough, amongst my section of our client group, as soon as they had extra cash, a whole lot of them, without my intervention, I might add, as soon as they had extra cash from higher wool prices and whatever else, they recognised straight away that they would put a proportion of that into lime, and they've put thousands of tons on. It's been a very interesting. I mean, without even questioning it, like that's the one thing that they knew they hadn't been doing. I mean, you know, they got straight into it. It's quite interesting.
Okay, great. Well, that was a good question. I think a very good question, and got some good comments there. Look, Jock asks, what are the panel's thoughts on spreading lime in pellet form, calcipril, to lift pH in native grass country to eventually spread superphosphate?
Well, I mean, you know, let's always look. I'd go back a step from that and say, what's the pH of the country now? How low is it? Right? If it's more common practice for us, if we come across a new client or something like that, or a new situation, a client buys a new property. I'm going to sound like a hypocrite now, and we find that the whole place is really low. You know, it's got reasonably low pH, but it's got really, really disastrous soil P. We tend to spend more of the initial cash that's willing to be parted with on the soil P, because in the short term, short term, it'll provide us with more returns. Okay, well we have that feeling anyway.
Makes it possible to afford lime.
And then maybe you're buying lime off the back of that. But so So what I can't really answer Jock's question because I don't know what the pH is, right? And I don't see, however, going back to Jason's answer to a previous question, if the pH was disastrously low, I don't know that I'd be putting calcipril on. I think I'd be putting a normal fine lime on.
Superfine.
Yeah, that's what I'd be doing because I think I get a better spatial. I get that better spatial spread of the liming effect.
Now, team, I want to ask a question just briefly. Is there any sort of school of thought that the third effect of acidic soils is the tying up of phosphorus? Is that something is that a real thing?
Yeah, Jason.
So that lower pH, iron and aluminium become more available, and both of those things bind up phosphate and make them less available to plants. And so liming a soil, increasing the pH, getting rid of that exchange with aluminium will free up some phosphate. Now, the next obvious question is, how much phosphate benefit do I get per ton of lime? And that's a really hard question to answer. It's not linear, it's not straightforward, and it's not the same for all soils. So, but you know, some soils, yep, increase the pH with liming, and you get phosphate being released that previously was bound up.
Okay, interesting.
In my experience, just looking at some data sets, it's usually a smallish amount of phosphorus. Is that reasonable to say? It's not a huge, like it's not, you're not going to go from Cold War 20 to 40.
Oh, no.
That's
So
what
if
I'm
you're
asking.
critical, it's not a problem.
So
yeah, true. Yeah.
If you're at a critical P, it doesn't matter what you do.
well,
It's a benefit. But
Yeah. It's a minor benefit.
sorry, what Nathan means by critical P is that the P at which we expect that we would achieve 95% of the plant's maximum response to phosphorus, right? So if we were around there, it wouldn't be any benefit. If it was lower than that, I had one of the clients call it a one-off sugar hit. So it's sort of like, yeah, you get a bit, but then it's once off, isn't it? It is true to say, what was our caller's name? Who was it?
No, that was
talking to?
no, that was from me.
Oh, that was from you, Dave.
Yeah.
So it is true to say, however, that as the soils acidify more and more, P fixation increases. That is known. So you expect as they neutralise, you'll get a reduction in you'll get an increase rather in the availability of P. But it is not. I mean, I've looked at some experimental data where they do lime by phosphorus responses, and usually they're pretty small, right, compared to the phosphorus response. So if you're better off to put fertilizer on, but you're better off to put super on if you want a P response than to put lime on an acid spoil expecting a big P response. It'll be there to some extent, but it won't be big. It won't be what you need.
Okay.
So again, soil test and manage your critical P.
Okay. Perfect. Thanks, guys. Now, okay, just to help you gauge your questions, we still got about 6 or 7 good questions.
Yeah, let's burn through them. I think there's how many people are still with us? Not many. Oh, there's still 68. There's still 68 of you listening. Let's go.
Yes, and they're the keenest 68, so we still got to do a good job. Now, good question from Frank. What about the idea of feeding dolomite along with trace elements assume the sheep or cattle for maintaining the room and balance with the excess being dispersed into the pasture?
Above my pay grade, I'm afraid.
I would say it's been a while since I did anything involving ruminants, but the rumen's acidic, and so it's going to neutralise the dolomite that's in the rumen. So the alkalinity is not going to hit the ground. Would be my guess at that, given some very vague notions of sitting in lectures many years ago.
All right. I was just thinking, if you wanted 2 tonne of dolomite, how much would that be down the throat of each animal, and et cetera, and what stocking rate? I think they'd be full of the stuff. I'm not quite sure. I don't know. Anyway, look, we don't. The answer is
that's fine.
We don't know.
Look, I've even got a question I can answer here, and
good.
This proves my extent of my technical ability in this area. Tony wants to know about the next webinar. It's not on the MLA website. Tony, everyone who's registered tonight is also registered for the next webinar, so you don't have to re-register. I have to update the webinar site every week, and you'll receive more information about that webinar, towards the end of this week and early next week. Question here from Terry: if we could somehow increase the microbial activity in high-producing soils, what will the activity have? Will the activity have an impact on soil pH? Could it be comparable to the application of lime?
The answer to that is no. And in fact, well, if you increase the microbial activity, you break down organic matter.
Yeah, they've got to have something to eat. You got to feed them something.
So they've got to have. So it's possible that you could an increase in microbial activity in terms of nitrogen release could actually increase acidity, possibly if it was leached on carbon cycle.
Well, you're growing the organic matter, it's decomposing, so that's an alkali in the surface. But yeah,
But you're on a decreasing trend rather than an increasing trend if your microbes outweigh the inputs of organic matter.
Yeah, you're still going to be limited by the organic matter, the food for the microbes.
Right. So the overall trend, if there were if there's more microbe activity, the overall trend would be neutral essentially with respect to as a function of microbial activity. So that nitrogen leaching one, I thought might be a problem, but I can't think of another.
So are you saying that there's no net effect on an acidification of soil, or is you still water nitrogen?
Yeah. You're saying we've got microbial activity. Theoretically, what would happen if there was more microbial activity? Well, microbial activity essentially just breaks down organic matter, right? That's what the activity would be that we're talking about. And if that was the case, then I can't see that it could possibly lead to a consumption of protons.
Yeah, that's right.
Fair enough?
Yep.
And so in that case, remember, we go right back to the equation at the start of the night that lime consumes protons, which reduces acidity. So if it's not going to consume protons, I can't see how it's going to affect acidity, I'm afraid.
Okay, no, for sure. Another question here from Steve. Is there any work looking at the effect of plantation forestry on pH and costs to re-establishing for pasture production?
So let's think about plantation forestry. Of course, massive amounts of alkali get removed, right? So I'm not familiar with figures. I could only talk theoretically. One would think that what's left behind is fairly acid. That doesn't surprise me that some of our clients basically are just looking at putting, they cut the stumps off and they want to create pasture, so they just put in cocksfoot because it's reasonably acid tolerant amongst it. So you do have how big would that be, Jason? Like, that'd be a fairly big hit to acidity, wouldn't it? Taking all that wood away, but it already would have acidified because most of it's just standing there as majority alkali.
Yeah, so I short answer, I don't know what the ash alkalinity of a
pine tree is. Yeah.
But I know a lot of pine forests have acid soils underneath.
Yeah, it's exactly right. Yeah. So the answer, the second part of the question, Dave, again was with respect to pasture.
What's the cost re-establishing the pasture production? What's the cost of that?
Yeah, well, I would have thought. In fact, I've just been asked this by a client, but we'd have to be looking at using lime. I think particularly. Look, I'd be testing the soil. Look, number one, test the soil, find out where it is. The costs would be those things, depending on how the forestry was cleaned up, whether stumps have been left, etc., etc. So it depends on and then you've got a situation whether you're either spreading. I don't think the cost structures are any different than from normal pasture. I suspect, however, that the lime requirement might be higher. I suspect that.
Okay. Great. Now, Jason, you've impressed someone in the audience, and hold on to your seat. They've declared a man crush on you, so you've obviously.
I think it's his. I think if they only knew how physically hideous he was.
That's his searing
But that's
good
okay.
looks.
No, we're about to put him back in his kennel after this. Back to the cage.
After all the heavy lifting he's done for you tonight, Jim. Gee whiz.
Yeah, I've done nothing. Oh no.
Yeah, no.
Go on. Give me a question, will you? Stop rubbing Jason. I'm sick of it.
I think a lady, Lisa here, she's making a comment. Use tolerant species as a stopgap for now, while you get around liming the whole property rather than a false sense of comfort by avoiding liming. The data set that Jim showed with the drop of 2 full units of pH in 55 years is actually an increase in acidity of 100 times.
Yeah, that's correct. Yeah, that's correct. It's a log scale. So that's a, I mean, I look at it, when I look at that data, I just look at the commensurate amounts of like aluminium. I think about the amount of aluminium that would be down there and how many, look, I don't know, well, maybe Jason will know, but I would imagine it'll take every one of those 55 years liming the surface and more, liming the surface at pH 5.5 to get over it, all right? So we've made, one hesitates to say that we've made a permanent change, but it's pretty close to it.
Okay, quick question here from Bernie. Just by
the way, Dave, just by the way, that soil before that 55 years, right, that would have grown loosened.
Yeah.
That's another way to look at it. That soil would have grown loosened. The one man loosened fan club here, but it would have grown loosened. So it's a pretty interesting, and it wouldn't have grown any loosen, and not a hell of a lot of phalaris, I would imagine, once it got, you know, to that 40-50% aluminium. So big opportunity cost there, I would have thought.
Okay, question from Bernie. Is direct drilling less likely to increase acidity than cultivating soils?
No, but what you get that stratification is worse with direct drilling, depending on the implement, whether it's tined or disc. Okay.
Rightio. Question from William. Can liming still be economically viable if the pH is 5.5 or higher?
Playing the short game, the answer to that would have to be no. In most of the systems that we've been talking about, playing the long, and I would have thought even the long game. I'm not aware of any results that show if you held it up to 6 that you give even faster amelioration of any acidity of depth, which could be the only, I would imagine, would be the only advantage of keeping the pH so high. Jace?
The only thing that comes to mind, like that'd be right. The higher you go, the faster the movement should down. And the other bit would be the cost of lime changing through time, or an application through time. Maybe it's cheaper to lime now than it will be in 10 years' time. In 15 years.
That's a bit of a gamble. We can't.
Yep.
I generally say at 5.5.
There's better things to do with your money.
Exactly right. I would think that there are if there are probably other more profitable areas, but again, you know, given the sort of master data, I wouldn't be saying, well, let it fall to 4.5 or anything like that. Okay, but at 5.5, there's probably better things to do with your money.
Look, Brad's asked a question here, and Brad, we've already answered this. We've already answered your question, Brad, about the whether we should spread small amounts of lime regularly or large amounts less regularly. So we might just have to move on. A question from James. James, would using gibberellic acid on phalaris in winter help stop acidification by sucking up more of the nitrogen? Good question.
Okay, so we know that with gibberellic acid that we probably have an advantage in around, I don't know, over 3 or 4 weeks, probably, I don't know, up to 400 kilos extra growth per hectare. Okay. I think, so the answer would be, if you multiplied that by any change in nitrogen concentration of the tops, it's likely that it would soak up a bit more. But I think the main problem in the middle of winter in southern Australia is the fact that there's such an excess of rain compared to evaporation, leading to leaching in the soil. And so now, by the time we get well into winter, mineralisation, those processes that lead to the accumulation of nitrate, they've slowed right up, okay, because it's too bloody cold, okay. So a lot of our nitrate is probably forming, well, there's a bump of the stuff that becomes available through mineralisation in spring, and then some depending on the summer-autumn rainfall pattern that becomes available then. I have to go back to Anna Ridley's work and think that I thought she showed, and some work I think done at the Wagga Institute showed fairly big nitrate leaching events. You know, when there was a bit of nitrate there, big nitrate leaching events in winter when you had really big rainfall events. And if that were the case, there's a bit of nitrate around, then it wouldn't matter really how fast the pasture was growing, the stuff would get leached. In principle, though, gibberellic acid treated pasture compared to non-gibberellic acid, I would expect more nitrate to be taken up. I have to say, though, I think it would have marginal effects on overall acidification. I can't prove it, mate, but that's where I'd be betting.
Okay, Charles. Look, I think we might have not been able to answer this. Charles asked whether going back to that tying up of P at low levels of as the soil becomes more acidic, he wanted to know how much extra P do you get from lifting your pH through liming and any other elements. I think the answer to that, correct me if I'm wrong, was a little bit, but not enough to make a big difference.
I think Jason really came up with the best answer to that, and he said that's, and I've read likewise elsewhere, that the amounts are highly variable and there's not a scientific way of predicting. Nonetheless, in any of the work I've read, it always seems to be the main response. There's a bigger response. There is a little bit of work to contradict this, but there is a bigger response to putting on P than freeing up P with lime. There you go.
Okay. Now,
in terms of growth, yeah.
The question from Rob: is there a liquid form of calcium that can address pH issues in the root zone if banded?
Yeah, no, the answer to that is lime slurries have been used, but we've got to go back to that original, right back to the start of the webinar 3 days ago, right back to the start of the webinar, where it's not the calcium that does the neutralization, it's the carbonate, all right? So another calcium source, such as gypsum or what else were there?
Calcium nitrate.
Calcium nitrate. They're not going to neutralize acidity.
The calcium's
right?
not.
The calcium's not going to neutralize acidity. So let's just go back a step. So yeah, there are liquid forms of lime. There are slurries that have been used, but I think the practice has pretty much been overtaken. But the practice hasn't been taken up because I didn't think it was economic. I'm not quite sure, or I'm not quite sure about the effectiveness.
Yeah, I know. I mean, I've done work with calcium bicarbonate, so lime, water, pressurized with CO2 to keep it as bicarbonate, and that worked really well. But just the engineering that would be required to put that into commercial context would be mind-boggling.
Right.
But in theory, it's possible. So in a lot of cases, you don't see that liquid limes being used because maybe the effectiveness of them aren't that great. The economics behind it isn't that great.
What about coverage would be a problem too, because you have to have a hell of a lot to get good coverage, wouldn't you?
Big nozzles. Yeah.
Okay. No.
But it has been tried, and slotting.
Yeah, slotting's been tried.
Yeah.
Can I just say, yeah, please, yeah, the biggest part of our answer to that would be remain mindful that it is actually the carbonate rather than the calcium that does the job.
Okay. Yep. So yep. Okay. Great. question from Dougal. This might be going back. This may be coming back in our knowledge a bit, or going back a little bit too far. Was the 1980 application in the picture that we can see there on the CSU lucerne plot a single application, or was that part of a long, long line of applications to those dark bands?
I'll get Jason to say, but my feelings were that they were big single applications. I can't, like I spoke to the person that did the initial trial. So those stripes are actually, you've got a dark green bit and a light green bit. They're actually in pairs, and they were split plots. So half the plot got limed and half didn't, of another experiment started in the 70s, and they got limed, a one-off application in the 80s, and that was it. So that's a one-off.
Do you know how much?
I don't know.
We don't. Yeah, we haven't
it has been published, but that was a lunchtime conversation that I.
Yeah, right.
Yeah. Oh, great.
Yeah, so
that's a great question. It's a one-off application, but we're not sure how much. Okay, that's interesting. Thank you. Okay, well, look, this has snuck up on us, but there's that's the last question, guys.
Oh no!
I know you'd be upset about that. Seeing it's only early hours of.
Considering I got to drive back to Tumut, Dave.
I'm about to go to Brekkie now anyway, Dave, so I'm happy.
You're about to start work already. I know. Look, there's been a lot of positive comments coming across the line here, like a few people suggesting that we should go for more wine. Thanks to the team. Terrific webinar. What a fantastic session. Great that you're reinforcing what we've learnt from Jason and Jim in the past. Someone's requesting a copy of the slides tonight. Jim, would you be comfortable if I sent out a copy of the slides?
Look, Dave. I just want to go through them and make sure I've attributed everything fairly, just in case I haven't, because it's hard to believe that but actually I put some of this together in a hurry. I just want to check this. I just want to check the slides and make sure that I've properly attributed, like where data's come from and things like that. And when I've done that, I'd be quite. I wouldn't care. I don't know what the copyright position is, and frankly I don't care. But I think I should always attribute. That's all. And I know there's a slides there where there's nothing there. So let me do that, I think the answer would be I'd have no problems whatsoever.
Yeah, we've got another with Lisa Castleman. She's also a big fan of the lucerne. So you've got two in your club now, Jim, and Johnny Francis, another home sacket counterpart. He was taking. He's listened to us all the way from Bright to Wagga, so he's found it very interesting. He thanks you guys for knowledge this evening.
Good evening, John. Enjoy the trip.
Look, so that's the last of the questions. Don't forget, for those who are signing off now, which I think there'll be a rush for the swag, please do take 2 minutes just to do that survey. If you've enjoyed and found tonight valuable, let us know. If you've sat around for the 2.5 hours and you found it a complete waste of time, apologise, but you're welcome to let us know that as well.
Blame Jason.
And look, thanks very much to Jason for participating tonight. As you've been more than a wildcard entry. You've definitely contributed a lot of knowledge. Nathan for coming all the way down from Tumut and being in the room to keep Jim on the straight and narrow. Thank you for that and for contributing your knowledge. And most importantly to Jim for pulling together such a comprehensive overview of the things we need to know when considering whether or not we should be liming in our systems. So on behalf of the audience and MLA, and thank you very much for that. To the audience, thank you for being part of it. And to MLA, thank you very much for funding it. So I think we've got a good three-way relationship going on.
Right.
Okay.
Thanks, mate.
Cheers.
Okay.
Bye.
Bye-bye.